Influence lines are a very efficient tool for representing what happens at a specific point in a structure as load travels across it. So in this example, we're going to construct influence line for a beam, and we're going to use the basic method or a table of values method. The key concepts we're going to use are calculating internal loading at a point in a structure and constructing an influence line from values at certain points. And here's our beam. It extends from the pin at A, across a roller support at B, and cantilevers out to the right. We're going to construct an influence line for the shear at C using the basic method or table of values method described in section 6.1 of your text. And here's our approach. Since we're using the basic method, first thing we need to do is decide the locations where we will apply the unit load. Once we've decided those locations, for each one of them, we'll apply the unit load and calculate the shear at point C. Once we have all that information, we're ready to construct our influence line. Let's get started. So we start by evaluating where to apply the unit load. With more experience, we'll be able to identify the minimum number of places to apply the unit load in order to construct our influence line. In this case, I'm going to take a few extra just to make sure. To identify all the points we choose, I'm going to identify my x coordinate as starting at A and increasing to the right. The places we'll apply the unit load are at A, at 2 meters, just short of 4 meters, and just beyond 4 meters, because with an influence line for shear, we have to look just on either side of the point. Come out to 6 meters, 8 meters, and all the way at the end at 12 meters. Step 2. Now we're ready to apply the unit load. And calculate the shear at C. For our first point, we're going to apply our unit force at point A, or an x of 0. We'll have a vertical reaction AY, vertical reaction BY, some moments about point B. I'll choose clockwise as positive for my summation. It's my choice, and I think it'll keep the algebra a little more simple, because then AY acts in the positive direction, and we get AY is a positive 1. So it's in the direction we originally drew it. Now let's cut our beam at C and find that shear. We'll keep the left piece. We have our reaction at A. our unit force, our unknown shear at C, and the moment at the cut. Well, some forces in the y. We'll take up as positive. We have the vertical reaction, which is positive, the applied force, which is negative, and the shear at C, which is negative. So the shear at C is 0. Now we'll put our unit load at 2 meters, which means it acts roughly here, and we have vertical reaction AY, vertical reaction BY, some moments about point B. Again, I will take positive as clockwise for my summation, so that AY is in the clockwise direction. The unit force is now through 6 meters. And so AY is a positive 0.75 in the direction drawn. Now we cut it at C. I'll draw the left piece again. I have my vertical reaction, 0.75 up, my unit force of 1 down, my unknown shear at C, and the moment. We'll sum forces in the y direction. We'll take up as positive. We have the reaction at A minus the unit load minus the shear at C. The shear at C is a negative 0.25. And so when the unit load is at 2 meters, this is our shear. Now we move the unit load to point C. We're going to start with a point just a little bit to the left of point C, so we'll call that 4 minus. We'll have reaction AY, reaction BY, and our unit force at C, just a little bit to the left. So let's sum moments about point B. Again, we'll take positive as clockwise, AY through 8 meters minus the unit force through 4 meters. AY is a positive 0.5 in the direction drawn. Great. Now we'll cut it at C. We'll keep the left piece for our free body at our vertical reaction at A of 0.5. We have our unit force, which is just to the left of point C. So it's on our free body diagram right at that edge. The shear at C and the unknown moment. We'll sum forces in the y direction. We'll take up as positive. We have the 0.5 at the reaction A minus the applied load minus the shear at C. The shear at C is negative 0.5. So when my unit load is just to the left of point C, my shear is a negative 0.5. Now let's look at that unit load. A little bit to the right of point C. Well, when we do that, it doesn't change my moment equilibrium. So AY is still 0.5 up. Let's cut it at C. Keep the left piece. We still have 0.5 for the vertical reaction, but now the unit force has moved to a little bit to the right of point C, so it does not show up on this free body diagram. We have our unknown shear at C, the unknown moment. All sum forces in the y direction will take up as positive. We have 0.5 at the reaction minus the shear at C. The shear at C is 0.5. This time it's positive. So when the unit load is just to the right of point C, we get a positive shear of 0.5. Now we move the unit load to 6 meters from the end, which puts it about here, which means it's 2 meters to point B, where we have reaction BY. And over here we have reaction AY. So let's sum moments about point B, as we've been doing all along. We'll continue to take clockwise as positive. AY through the 8 meters minus the unit force through 2 meters gives us an AY equal to positive 2.25 in the direction we drew it. Now we'll cut it at C. Keep the left piece. Our vertical reaction of 0.25. Our unit force is way over here, so it's not on this free body. Shear at C, unknown moment. Sum the forces in the y direction are 0. We'll take up as positive. We have the vertical reaction minus the shear at C. The shear at C is a positive 0.25. So when the unit load is at 6 meters, we have a shear at point C of positive 0.25. Let's move our unit load to 8 meters next, which puts it right here above reaction BY. Over this end we have reaction AY. We'll sum moments about point B. Again, we'll take clockwise as positive. AY through 8 meters, and that's all that contributes. So AY is 0. Now we cut it at C. We'll keep the left piece. We have 0 for our vertical reaction. The unit load is off of this free body. We have our unknown shear at C. Sum forces in the y equals 0. The shear at C is 0 when the unit force is at point B. And our last place we're going to put the unit load, at the far right at 12 meters. So it sits way out here with the vertical reaction at B and the vertical reaction at A. We'll sum moments about point B. Hopefully you're beginning to see a pattern here. The process we'll follow remains the same as we create the table of points. This time the unit force also acts clockwise, so it's going to be a positive contribution, and it's 4 meters from point B. We'll solve AY and find it is a minus 0.5, opposite the direction we drew it. We'll cut our beam at C. We'll keep the left piece as usual. Our vertical reaction at A is now a negative 0.5. No unit load on this free body. unknown shear. Some of the forces in the y are 0. We'll take up as positive. I have a negative 0.5 vertical reaction minus the shear at C. So the shear at C is a negative 0.5 when the unit load is at the far right end, or 12 meters from A. We are now ready to construct the influence line. We're going to start by tabulating all of our results. We have the location of the unit load. We called that X. And then we had the shear value at C that we calculated. When the unit load was at 0 meters, or at point A, we got a shear of 0. When we move that load to 2 meters, we got a negative 0.25. When we moved it to just to the left of point C, we got a negative 0.5. When we moved it just to the right of point C, we got a positive 0.5. And we continued out halfway between point C and point B. We had a positive 0.25 for the shear. When the load got to point B, directly over the support, we're back to 0 shear. And then when we step all the way to the end of the cantilevered part of the beam at 12 meters, we get a negative 0.5 shear generated at point C. Now we're ready to construct our diagram, our influence line for the shear at point C. Remember, this picture is only telling us about the shear at point C. And at x equals 0, we had a 0 value. At x equals 2, we had negative 0.25. And x equals just a little less than 4, we had a negative 0.5. And then we moved to the right side, and it was a positive 0.5. And we had a positive 0.25, a 0, and a negative 0.5 again. We know that for a determinate structure, the influence line will always be made of straight line segments. And as we connect these dots, that seems to hold true, which is a sign that we have quality data. We'll put our labels on our diagram. And now let's go back and review how we got to this point. When constructing an influence line by the basic method, or the table of values approach, we have to decide where to apply the unit load. And in this case, we chose 1, 2, 3, 4, 5, 6, 7 locations. But in hindsight, we probably only needed these 2 and this one. Because when the unit load acts directly over a support, there are no internal forces generated in the beam. It goes straight into the support. And we knew how to connect them with straight lines, so this point and this point were unnecessary to us. But it was still a valuable exercise. After deciding where to place the unit load, our first point was at A. We calculate reactions, AY, due to the unit load. We cut it at C, and we keep one piece. In this case, I chose to always keep the left piece, and we found that our shear was 0. Then we move the unit load over. But the process of calculating the reaction is the same equilibrium equation. We take it about the same point, It's just the distances that change. We cut it at C. Again, we apply the same vertical equilibrium. And we continued that same process over and over and over again. Here we are with the unit load just a little bit to the left of C and a little bit to the right of C, and it gives us two very different shear values, one negative, one positive. Then we moved to 6 meters, calculated the shear. We moved the load to point B, and as I mentioned earlier, when the unit load is over the reaction, it goes straight into the reaction and we don't get any shear in the beam. Then we moved all the way out to the far right and we calculated the shear. With all those results, we then created a table of values. We used that table of values to plot our influence line, connected it by straight line segments, and put the labels on it. Well done.